Hello and welcome to the 2020 Holiday Science Show. As you can see, this year it looks a bit different, but we still managed to pull it off. In this video, we will be doing a series of experiments on a variety of different topics. First, we have Mariah Clark, a senior, making a fire snake purely out of sugar and lighter fluid. Next, we have Nathan Schilling, who will be making bread using the power of farts. Then we have Damien Whipperforth, who will be using a series of vinegar experiments to turn a regular egg into a rubber egg. Then we have Brennan Cummings, a senior, who will be bringing us the sound of success with his homemade bass guitar. Then we have Jacob Cry, a senior, who will be leaving us floating with his series of demonstrations on density. And finally, Rachel Flickinger, will be lighting things up using potato power, nails, and pennies. And with that, let's dive right in.
Hi guys, I'm going to be teaching you about combustion reactions, also called burning reactions. You've obviously seen something burning before, but have you ever actually thought about what's happening when something is burning? There's actually a lot of chemical reactions happening, and I'm going to show you an experiment today, which I like to call the fire snake, which takes a look at some of the cool things that can happen. This isn't really something that you should try at home, but I'm going to show you something that you can do at home that's kind of similar. First, let's take a look at the materials I've got here. I've got an aluminum cake pan, and I've got a little bit of dirt in here. And that's just for this sugar and baking soda to sit on. I also have some lighter fluid, which I'm going to put a circle of in the middle, and then that is where I'm going to put some sugar and baking soda. Next, what I'm going to do is I'm going to start the fire. And again, this is not something for you to do. This is for something their parent would do. So I'm going to light that. And I'm going to light this. And let's take a look at what happens. Pretty cool, huh? Let's take a quick look at how it works. When I lit the sugar and baking soda, it started a combustion reaction. A combustion reaction is when the molecules that it's made of react with the oxygen, which is in the air, and it starts to break down into different materials. When I lit the sugar, it turned into two things mostly: carbon dioxide and water vapor. Carbon dioxide is the gas that happens when you breathe out. And water vapor is like when it's really humid outside and you can feel that there's water in the air. When I did this to the baking soda, it did the same thing. It made carbon dioxide and it made water vapor, but it also made something else. It made something called sodium carbonate. Sodium carbonate is the black stuff that the snake was made out of. The snake grew because the pressure from the gases being released pushed the sodium carbonate up. And that's why the snake grew. I think that's pretty cool. Now I'm going to show you something pretty similar in an experiment that you can do at home. You've probably actually already done it. Have you ever thrown a marshmallow in a campfire? What did it do? Did it turn all black and bubbly? I bet you it looked kind of like the sugar snake, didn't it? That's because this is actually very close to the same process. Now keep in mind, this is something that you need to have a parent with you because of the fire. Here's a quick look at what happens when you do that.
Okay, so making bread. These are the things that you're going to need in order to make bread. First, you're going to need yeast, and you're just going to directly add it to some water. Then what the yeast is doing is that the yeast in the water is now alive and it's growing and it's eating some of the nutrients in the water, and it's going to proof, which is the words that we mean for when it creates carbon dioxide. So what we're doing now is we're adding flour to the mixing bowl. This is going to be 1/2 cup right away here. And so what we're doing now is adding sugar. And so what we're doing now is we're waiting for the yeast to proof, and we're attaching the dough hook. The dough hook is important because it helps knead the bread while also mixing it. So you can see on the right that the water with the yeast in it is bubbling up, and the yeast has started to look a little foamy. And so that's how you know that the yeast is proofing. And we're pouring the yeast in. As you can see, the yeast and the water are pretty well mixed by this point, and so you know that they're proofed. And so immediately after adding in the yeast and your 3/2 cups of flour, you're going to pour in 2 more cups of water. So the entire process is going to take 6 total cups of flour, but adding them by halves, you're going to need 12 halves. And so if you look at the yeast, flour, water mixture, you'll see that there's bubbles forming already, and that's really important to the bread. So basically, as I add more flour here, I'm going to describe the process that the yeast goes through in order to create the carbon dioxide and the oxygenation inside of the bread. So basically what you can picture it as is the flour has a bunch of little nutrients inside it that helps the new plants grow. And so originally when you have the wheat, you're grinding up this flour, and the flour is ground up, and so all those nutrients are crushed down, but they're still there. And so when you add the yeast to the flour, the yeast just starts eating all those nutrients, and it transforms them into pockets of carbon dioxide, as well as other flavors that we really like in our bread. And so the carbon dioxide that it releases is really what makes your bread poof up. And so we'll see that later when we watch it rise. As you can see, there's starting to be some strips in the bread. And that is because there is the fibers of the flour and the fibers of the yeast are bonding together, and you're stretching them out. And so they pull against each other and they tear. So what we're doing here is we're adding another 1/2 cup of flour into the mixture, just so that it won't stick to my hands as badly, but also so that we can flour the work surface. So as you can see, I'm picking up the bread and making sure that some of the flour gets underneath it. And then I'm folding it back into itself. So I'm stretching it out, pulling it apart, or pulling it together. And so what the yeast does is that it loosens it up. So it's like when you go to sleep at night, sort of. And so then when you're kneading the dough, it's sort of like going for a run or working out, lifting weights. You're making your muscle tighter. And so what I just did here is I added this dough to a greased bowl. The greased bowl is important just to make sure that it doesn't stick to the edges. And so after that, I'm going to add this piece of cloth to cover the dough. And then I'm going to wait for it to rise. And so after it's risen for a while, I'm going to take it out. And as you can see, it's filled up this entire bowl. I'm going to plop it onto this baking sheet. So the first thing that you're going to want to do when you're shaping your bread is you're going to cut it into 2 pieces, because this one is probably too big for a single loaf. Now you could have the recipe and you would get half as much, and you could make that a single loaf. But since we've made so much, I'm going to make it into 2. So what I'm going to do is set aside one and just begin working with the first one. So what you see me doing here is adding corn flour to the bottom, or cornstarch to the bottom, corn flour to the bottom of the baking pan, just so that the bread won't stick when it's in the oven. And so what I'm doing right now is I'm making a baguette-shaped bread. And so when you're leaving it on your baking sheet, it's going to rise for a second time. So you leave it on the baking sheet for about 45 minutes for the second time. And the first time when you let it rise, you could go anywhere from an hour to about 6. I mean, you could leave it for a whole day if you wanted to, but it takes a while then. So you're going to leave this on there after cutting these slits for about 45 minutes to an hour. You could go as short as 30 minutes, but it doesn't rise as well then in its shape. And so what we're doing is, after it's risen for a little bit, is we're adding it to the oven. And when it comes out, it becomes this baguette. So what's happening inside of this pill bottle right now is that the yeast is beginning to break down some of the nutrients inside of the sugar. As it does this, it's filling up the bottle and the balloon with carbon dioxide. The yeast builds up bread based on the power of a bunch of little small pockets of carbon dioxide. They're dispersed really evenly throughout the bread. Now, one thing that you can do to make the effectiveness of this experiment better is to have your yeast pill box be on a heated blanket. And the reason for that is because yeast grows best in an environment that is about 80 to 90 degrees Fahrenheit.
Hi, so we're going to be doing a fun little experiment with vinegar. So we have our 3 jars of vinegar here, and we're going to do 3 different experiments. So vinegar is a diluted acetic acid. So if you do choose to do these experiments, please be careful. So we're going to do our first experiment with baking soda. Now, baking soda is a sodium bicarbonated substance. And if you've ever done a baking soda volcano, this is what the reaction inside looks like. And if you've never done one, you get to see the reaction. So we're going to take a small spoonful of baking soda. And now I have a towel right here. You're going to want a towel if you do this. You're just going to drop it in. And it all fizzes out. So that is because when the baking soda and vinegar mix, they create carbon dioxide and fizz and bubble like this. It's kind of like when you shake a can of soda and then open it and it just goes everywhere. It's all that carbon dioxide building up inside the can and then you're releasing it. So our second one is with a simple piece of sidewalk chalk. Now, sidewalk chalk has calcium carbonate in it, just within it, and that'll also make carbon dioxide, making it fizz. So small bubbles should form around the sides of the chalk. So we'll put that in. I don't know how well you can, you can see it dissolving. So this is just simple Crayola brand chalk. You can see all the bubbles. It's kind of squeaking because of the bubbles being trapped inside. So there's that. And once again, that's with the vinegar mixing with the calcium carbonate, making carbon dioxide, making the bubbles. And our last one, just move these out of the way, is with an egg. Now here I have a larger jar of vinegar, and if you do choose to do this one, you're going to want the egg fully submerged. So the egg is also made, the shell is also made of calcium carbonate, and when you put it in the vinegar, After 24 hours of the egg sitting in the vinegar, it will be soaking in all that vinegar, and like with the chalk, the vinegar will dissolve the calcium carbonate. So basically, the eggshell is just going to disappear. And actually, since that one's going to take 24 hours, I have one that is done. So here it is. This is what the eggs look like. Shell, you can see, it's over here actually, the yolk inside moving. And it's squishy because the hard shell has dissolved away. So all of the inside of the egg is still there. This is the membrane that's on the shell. Like when you crack an egg open and there's that little flimsy piece on the inside of the shell that you can peel off. That's what this is. It's holding everything in right now. And since the vinegar's kind of strengthened it, it's able to hold it and you're able to squish it a little bit. Do be careful because the inside's all there. And speaking of that, we're going to pop it. So ready? Just this right here. 1, 2, 3. So yeah. The egg is still completely there. And then here is that membrane that was on the shell. Kind of play with that. So I let this egg sit a little longer than needed. So the inside is a little solidified too, like this. I'm trying to pull it over more. I can't really pick it up because it's all liquids. But this stuff starts to solidify as well. And it's like this weird jelly consistency. So yeah. If you want to do these at home, go right ahead. You just need vinegar, baking soda, chalk, and an egg. Yep. Thank you.
Have you ever been in a band class or just been listening to music or even playing some of your own in general and wondering, how is this instrument, how is this making sound? What is sound? Well, sound is just vibrations through air, solids, liquids. We're most familiar with air, but we can't experience sound through solids. If you have tied 2 cans with a piece of string and talk to them, that's sound transferring through a solid material, the string. How do we make sound with instruments? Well, it's just vibrations again. And one of the easiest ones to understand, in my opinion, is strings. Now, I have a string instrument here. It's called the bass. It's got strings, as you can see here. But if you notice something, that string is a lot lower sounding than that string. Why is that, though? Well, to put it simply, one of the factors that affects that is tension. This low string here is under less tension than this string, making it so it can more freely move. So it can move. Now, you also notice it's got these metal bars going across it. What do those do? Well, they make it sound higher the lower down you go. Why is that? Well, it's because I am making the string shorter, so the string has less space to move, so it goes faster, it vibrates faster. The faster the vibration, the higher the pitch. Because sound is vibrations. Now, this may be hard to demo with and mess around, because it's very fixed into what kind of pitches it can do, and they're kind of expensive, so I made a cheaper alternative for you guys that you can do at home. It's very simple. Grab a box like this, have your parent poke a hole in the lid, tie a string to it, secure the string, secure the lid back onto the box, and make sure the string's secure too. You don't want it to fly and hit your face, and, well, if you can see here, tie it to a pencil. If I pull on it hard, it makes a higher pitch, and if I loosen my grip, it sounds a lot lower, right? Now if I go here and make the string shorter by winding it around the pencil, I can get a much higher pitch than I could before we're using the full length of the string. But I can also still get it lower. So, I ask you to try this at home, because it's fun and mess around with it. See what kind of sounds you can make. If you can see if you can actually make a song using it. Have fun.
Hi there. Today I'll be talking about density. So density, simply put, is a sciencey way of saying how much stuff is in a certain area. Now, this may sound a little confusing at first, but we see it all around us in our everyday lives. So let's take this rock and this ping pong ball, for example. They take up about the same amount of volume. As we probably can guess, this rock is way heavier than this ping pong ball here. That's because this rock has more stuff in it. And because of this, we know that the rock is more dense than this ping pong ball here. And density is not just about solids, we can also compare it to water. So as you can see here, these two glasses of pure water have the same density, right? Because they're the same volume, they're the same size, and they've got the same amount of water in them. And now this ping pong ball, as we know, is really light, so it's very, very not dense. And so we put it in water, it floats just like that. But now if we take this heavy rock, this dense rock, drop it in, kasploosh, right to the bottom it sinks because it's more dense than the water. But what if we took something in between these two? What if we took something that was like a medium density? How about an egg, for example? Now, if we drop this egg in the water, it's kind of heavy, so let's see what happens. Well, you can see it still sinks to the bottom. How do we make this egg float then? How can we change the density of water? Well, it wouldn't work to add more water into it, because that just changed the volume. What we need to do is add more stuff to it to make it more dense without changing how big it is, how big the water is. So let's try this. If you want to experiment with this at home, all you need to do is take a cup of water here, pour it in, and get yourself some salt. And you take 2 tablespoons. So there's 1 tablespoon. And there's 2 tablespoons. And your parents can help you out measuring wise. And now, as you can probably guess, or as you can probably connect, the ocean is just like this. It's salty water. So what we're doing right now is making our own little ocean at home. And so you're going to want to stir up the salt really good like I am here. Get it scraped off the bottom and everything to make sure it's all mixed in, just like the ocean. It's all mixed up. And now that we've done this, you can kind of see that these 2 lines are about the same. So it's the same volume, it's the same amount of water, but this water here, as you can easily see, has a lot more stuff in it. It's got the salt in it. It's our little ocean. So now if we take the egg, it still sinks in this water here, right? But if we take this egg and put it in this more dense salt water, you can see it floats right up to the top there. And that's a perfect demonstration of how we can float in the seawater. And that brings us to what I'm going to show you next. There's this special sea in Europe called the Dead Sea that has tons of salt in it. It has so much salt in it. And so people go there all the time so they can float in there super easy.
Hello! So today, for my experiment, we're going to make this little light glow using only potatoes. And so how do we do that? Well, what you need is you need a potato, right? Just a big one. You want a big one. You want a whole bag of potatoes because you're going to need a lot of potatoes to produce enough electricity to light this light. And then you're going to need a galvanized nail, which is, as you can see, it's kind of not shiny. That's what shows you that it's galvanized, which means that it's coated in zinc. And that's really important for this project. Then you're going to stab it in one end of the potato, right? Then you're going to take a penny, or you could use some of this copper wire, that works too. And then you're going to stab that in the end of the potato as well. So one end is the nail and the other end is the penny, right? And then you're going to need alligator clips. I have lots of them. I got them on Amazon. They were like a package of 30. I think it was like $11. You're going to need these alligator clips because these are going to connect to your potato. And so you're going to clip an alligator clip on one end of the potato. And then you're going to clip another one on the other end, on that penny end. There we go. That penny fell out, but it's freshly stabbed in there now. So you have, you know, an alligator clip on each end, right? And so we're going to show, you're going to want the nail side, which is this red one that is attached to the nail. You're going to want that on the short end because there's two different sized tongs on this. There's a short end, which is right here, and then there's a long end, which is right here. So you're going to want that, this red clip, that's the zinc one. You're going to attach it to the short end. And then you're going to attach this green one, which is the penny end, to the long end, right? And so these are both going to be connected, right? And as you can see, nothing lit up. That's because one potato doesn't produce enough electricity. So one of these lights is 3 volts of electricity. A potato only produces about, you know, a half a volt. So you're going to need lots of potatoes. And I'm going to show you in these next couple of clips, you know, what happened when I made an entire circuit of potatoes. So yeah, we'll be right back when you see me put that together. Alright, so that was my potato battery. As you could see in that short clip I did, I had 10 potatoes and they were all attached with alligator clips, forming a circuit, right? And as I showed earlier, one potato wasn't enough power to power one of those like tiny LED lights, right? It takes 3 volts and it took all 10 of those potatoes to produce enough light. And so how does this happen? Like, how can a potato like this, just a potato with a nail and a penny in it, how can that be as powerful as something like this? Well, this potato has a positive and a negative side. And if you know how batteries work, right? The battery has a negative on the top, this flat part, and then it has a positive part, right? That produces a current, right? And in a battery, you know, when you attach it into something, that's going to run power through this negative part, through the positive part, and that forms a circuit. That circuit produces voltage. That voltage can make something light up, or it could power like a toy that you had or something. Now this potato is the same idea, right? We have our negative part, and then we have the positive part, which is that copper. And what happens is, using alligator clips, you're creating a circuit, right? So the power is going to run through this negative part into the positive part, and then that's going to power this light. It's forming a circle, right? It runs through the negative to the positive, and what the potato is doing, what the potato is acting as, is basically in a battery, right? This is an alkaline battery. There's a fluid inside of it, and that acts as an electrolyte. And the electricity can pass through this electrolyte from the negative to the positive side. And the potato is acting as that fluid in the battery. And what's really interesting about this is that you only need simple materials to create something as complex as a battery. Of course, you need lots of potatoes to do this, but it's just a really cool thing because it's just like a battery, and you can power lights, you could power a light bulb, and all it takes is a nail, some copper, a potato, and some alligator clips. Today, I'd like to say a few thank yous. First, thank you to all the members of Science Club, everyone who spent extra time recording these videos, planning these videos, and trying to think of experiments, even with your life in disarray. Thank you, because it matters to me that everyone did it. I'd also like to say a special thank you to Adam Steinberg, our advisor, our impromptu video editor, and our die-hard supporter. Thank you. We wouldn't have been able to do it without you. And finally, thank you to all the people there at home today who are watching this video. We really appreciate everyone who supports it, and it's nice to bring a little bit of joy and some science to everyone's life. Happy holidays, stay safe, stay curious, and go out and do some science. Thanks again.